Okay, so we're working on the absolute value of a function. We have this function, y equals 2x minus 6, and we have some values of x here, along with corresponding y values here. And what we want to do is complete the table for the values of y equals the absolute value of 2x minus 6. So what does absolute value mean? What do I do with these y values? Make them all positive. Okay, so this will be 6, 4, 2, 0. If they are positive, they just stay that way. But if they are not positive, then we make them positive. Use the table of values to sketch the graph of y equals 2x minus 6 and y equals the absolute value of 2x minus 6 on the grid shown. And then how do the graphs compare? So let's do this one in red. Okay, so we've got 0, minus 6. We have 1, negative 4. 2, negative 2. 3, 0. 4, 2. 5, 4. And 6, 6. What do I do with those points? Put a line through them, right? We join them with a straight line. Since they all lie in a straight line. All right, actually, I'm going to kind of cheat a bit and just stick a few more points in. Okay, and then arrows on each end as well, right? To indicate that we have that line, these points are on the line, and the line continues forever in both directions. Okay, let's use green, and we will graph y equals the absolute value of 2x minus 6. So instead of 0, negative 6, we have 0, 6. 1, positive 4. 2, positive 2. 3, 0. That points on both graphs. 4, 2. 5, 4. And 6, 6. So we can see that we share some of these points are shared and some are not. We're going to sketch this graph. And I'm going to end up putting the green line here on top of the red line, right on top of the existing red line. So the question is, how do the graphs compare? So how do the graphs compare? Part of them is the same. Part of them has a red and a green line, but the other part, the red line and the green line, are different. So how does this green line here compare to this red line down here? It's a reflection, yeah. Where is it reflected? Where's the x-axis? Good. So the reflection in the x-axis. So the negative part, of y equals 2x minus 6 is reflected in the x-axis. Okay. Now, that kind of goes with what we know the definition of the absolute value function is, right? So we know the definition of the absolute value function. So say the absolute value of a is equal to a if a is greater than or equal to 0, and it's negative a if a is less than 0. And all right, so let's say instead of a, let's make that an x. So if that's an x, then that's negative x. And we know that when we put a negative in front of the x, that we reflect it in the x-axis, right? So we take negative 6 here, and we turn it from negative 6 into positive 6. Okay? That's really just the definition of absolute value. If the function evaluates to give you a negative value, then you take the negative of that and make it positive. the effect on a graph is that it's a reflection in the x-axis. Okay, questions?
Can I explain that again?
That's just from the other day about absolute value. So if you look in your textbook for definition of absolute value, it comes out like that. It just says, if it's positive, leave it. If it's negative, then take the negative of it. A negative of a negative becomes positive. Okay, and I think that's all there is on that page, so let's move. Complete the table of values shown for the function. So we have y equals x squared minus 6x plus 5. So we know that that's a parabola. We know it opens up. We know it's not in the best form for graphing, right? I mean, if we change that to vertex form, it would be a lot easier to graph. But we can also graph from a table of values. Now, as I do the absolute value, what am I looking at here? Which of these changes?
The negatives.
The negatives here, right? So the positives just stay. That's 12, 5, 0. This becomes positive 3, positive 4, positive 3. And these guys stay. So again, let's use red for this function. Okay, we're going to graph this using the table of values. So when x is negative 1, we have positive 12. When x is 0, we have 5. When x is 1, we have 0. When x is 2, we have negative 3. When x is 3, we have negative 4. That looks like the vertex there, because now we turn around back up again. At 4, we're back to negative 3. At 5, we're at 0. And at 6, we're at 5. And at 7, we're back to 12. What do I do with these points? Join them up. Smooth curve, right? Arrows on each end, indicating that it goes on. And we're going to graph the absolute value function. We'll do that in green. So the only thing that changed, this point's the same, 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 this point's the same. We had those three values change. We had these negative values here change and become positive values. So we have 2, this negative 3 goes to 3, this goes up to 4, this one goes to here, 3. We can join the points. So it's green on top of red. Then we've got this little kind of a bounce off the axis. We can think of it as a bounce, right? But really it's a reflection again. Bless you. So this is simply a reflection of the part of the graph that's below the axis down here is now reflected and is now up above the axis up here. Okay, any questions? Use table value to sketch the graph on the grid shown. How do the graphs compare? So how do the graphs compare? The negative part of the graph is reflected above the x-axis. So the negative y values become positive, reflecting that portion of the graph. In the x-axis. Okay, then a little blurb at the bottom. The graph of y equals the absolute value of f of x is the same as the graph of y equals f of x, except the portions of the graph y equals f of x that are below the x-axis are reflected in the x-axis. The points on or above the x-axis are said to be invariant points because they remain unchanged, so they don't vary, right? They stay the same. That's invariant because they remain unchanged after a transformation. Okay, any questions on this one? Nope. Okay, let's go on. And at the top, again, it's just the little blurb about the invariant points. Because they don't vary, they remain the same after transformation. Graph of y equals f of x is shown on the same grid. Sketch the graph of y equals the absolute value of f of x. So do we need a table of values now to sketch this? No. Okay. So all we do is say what? Well, this part's going to stay the same, the part that's above. So running along here, and use blue this time. What I can do is find some points, right? If I want to draw this accurately. So say at 12, that's negative 2. I'm going to make it positive 2. And at 15, that's 4. So negative 4, I'll make it positive 4. And at 18, it's negative 6. So I'll make that positive 6. And again, all we do is reflect. So we're reflecting this line here in the x-axis, changing all the negative values to positive. And that's what we end up with. Okay, questions? Seeing none, let's do the next one. This time we have the partial graph of a parabola. I mean, we don't show the arrows on these because we can't get arrows on these graphs. So we know this opens down. It's a parabola opening down. So these values here, the values above, will stay the same. Sketch over them in red. Right, and the values that are below. So again, we can choose a point, right? Let's take this point at 2, negative 6 will become 2, 6, right? Just to give me an idea as to where I need to be going through. And similarly, this point at negative 5, negative 6 becomes negative 5, 6. Now I'm not going to draw a straight line here. It still is a curved line. This is a curved line, so I need to draw a curved line. But it's a fairly straight portion of that curved line. Okay, so what results? This part here is gone. As far as the absolute value goes, right? And we have reflected these squiggly lines up above. Okay. Questions on either of these two? Nope. All right, let's slide down. So here we're looking at two more graphs, and again, what's going to happen? The negative portions, the portions down here, which I will draw, cover over in red, will simply be reflected up above, okay, which I will do in blue. And so it's going to go like that. This portion here will go up here, and this portion here will go up here. Okay, and what are we doing? We're basically losing these parts. So no negatives, right? In an absolute value graph, there will be no points below the x-axis. Unless you actually shift that graph down. Remember how we moved parabolas down? You could take an absolute value graph and move it down, and then you would have points below. Okay, but right now we're not doing that. Okay, so same thing here. I want to take this portion of the graph here, and this portion of the graph here, and just reflect them up, right? Reflect them in the x-axis. So I'm kind of looking for that's about 2, 5. So that's about there. So this portion will look like this. And the same thing, right? It's just looking for a point on this so that I can be reasonably accurate. And there we go, and then this. And our graph is simply the portion above the x-axis. Okay, so any questions? So given a graph of a function, you should be able to sketch the graph of the absolute value of that function, right? Given a table of values, which graphs a function, you should be able to sketch the absolute value of that function. Okay, any questions? Seeing none. The graph of y equals the absolute value of f of x is shown. So this time we have the absolute value of the graph. Determine the possible equations. And the important word here is equations. Okay? There may be more than one because either this part here, the left part here, was reflected. So it was originally down here, right? So let's draw that. Say, well, what if this part were down there? Then, okay, I'm just going to pick a point.
What if you did the other line and put it down?
Yeah. Well, I could do that too. So it's either or, right? So let's do them one at a time. Either the left half was down below, that's the red line that I've drawn, and then was reflected above, which gives me this red graph here. So let's find the equation of the red graph. Okay, so this graph now is y equals f of x. What is its equation? Well, it's a straight line, right? We should be able to do it by slope-intercept. What's the intercept is 2. There's this point here, so that goes up 2, and 1, 2, 3, 4, and right 4. So that's a slope of 2 over 4. Okay, which we would call 1/2, so 1/2 x plus 2. Okay, so that's the first possible equation, right? There are 2 of them. So what I'll do is let you write this down, and I'm just going to erase it all, and we'll just start over again and say, all right, what if the other half? What if the right-hand side were the side that was reflected?
X plus 2 in brackets or
Nope.
y?
It's mx plus b. This is a straight line. Straight lines are in the form y equals mx plus b. M is the slope and b is the y-intercept. Okay? So this is the equation if this half, if the left-hand half of the graph were originally down here, was reflected up to become the absolute value graph. Okay? Or, so I'm just going to erase all this and we'll just start over and just do, well, what if it was the other side? Break the leg. Okay, what if this half of the graph were the part that was reflected up? Then it would be down here. And again, I could just pick some points. Okay, so now we're looking for the line, the green line, right? So either the red line that I first drew was, we took the absolute value of that, which reflected the left-hand side up, or this green line, which I've now drawn, we take the absolute value of this equation, that will reflect this section here in the x-axis, giving the black line. So what's this equation? What's the equation of this graph? Okay, so again, we'll do y equals mx plus b. Okay, your y-intercept is -2. So it's going to end with -2. That's your plus b. And the m part, the slope. down 1, right 2, be negative 1/2 x minus 2. Okay, so we can see there are two possibilities here. And all it's doing is taking the graph, finding where it hits 0, finding this and saying, well, either this half was reflected up or this half was reflected up, and running through the two possibilities. Okay, question? Nope. Okay, let's do the same thing. We have this. So either the little hump here was reflected up, which means that originally it would have done this. Okay, so let me just erase that part. Okay, so either this was the original. Well, let me fill the whole thing in red. So either this was the original, this part just stays positive, right? These parts here, these arms that I just drew in here, these are the invariant points, right? And these points are not. You know, the hump here is not the invariant point. Easiest form for a quadratic is to use vertex form, right? So we got the vertex, which is at 2, negative 2. If I go over 1, I go up 2. So that tells me there's been a stretch by a factor of 2, right? It opens up. So y is equal to positive 2, x minus 2, quantity squared, minus 2. Okay? Now you can verify that by graphing, right? You could pull out your graphing calculator and graph this, see if that's what you end up with. Right, let's check it again. Go over 1, up 2. If I go over 2, I should go up 1, 2, 3, 4, 5, 6, 7, 8. Okay, which is right. So that tells me that the a value is a 2, right? We've got a vertical stretch by a factor of 2. So if you draw the graph of the absolute value of 2, x minus 2, quantity squared minus 2, you'll end up with, and let me just erase everything now. Okay, give me a moment, make sure you've got that all written down. So if we graphed y equals the absolute value of 2x minus 2 quantity squared minus 2, then we would end up with this graph here, right? The black graph. Okay, so that's possibility number 1. What's the second possibility? How else could this graph look? Could open down, in which case these points will be the invariant points because it opens down, and these arms here would have been reflected, so we're simply going to reflect them down. And now what we're going to do is find the equation of this graph. So again, vertex form equation, right? The vertex now is at 2, 2. It opens down, so y equals negative 2. It's the same shape as the original graph, right? So, but it just opens down. So it'll be negative 2, x minus 2 squared plus 2. Okay, so that's the second possible equation, right? We have two different possible starting equations, okay, one of which, or both of which, would yield the graph, the resulting graph we saw, the black line graph. Questions? Right, so you see this on a test, you're going to be, yeah, okay, fine, I can find you both equations, right? Okay, let's move on. For y equals the absolute value of negative 3 halves x minus 3, we're going to start by sketching the graph, or sorry, in order to sketch the graph of this, part A, in order to sketch the graph, we will first sketch the graph of y equals negative 3 halves x minus 3, right? Without the absolute value. We're just going to sketch this graph. And I could do that using slope and intercept, right? So the intercept is -3. The slope is -3 halves. That says go down 3, 1, 2, 3, go right 2. Go down 3, 1, 2, 3, right 2. Can't go any further, but I can go up 3 and left 2, up 3 and left 2, up 3 and left 2, up 3 and left 2. I like to fill in as many points as I can, right? I mean, that way I know I'm drawing an accurate graph. I'm not just going to draw, take 2 points and just say, well, it's a straight line. I just need to join those 2 points with a straight line. And when you're sketching graphs on a test, the more of these you show, right, it's easier for us to forgive, slightly wobbly lines or that, right? Okay, so we just got to join these with a straight line. So, it wouldn't hurt for you to bring a ruler with you. Tom, wake up. Wouldn't hurt for you to bring a ruler with you to be able to draw a straight line, right? On the test, you're going to be able to draw a straight line. Okay, so sketch the graph first by sketching. Okay, so we've sketched this graph. Now we know that the negative portion here is going to reflect up. So I'll do that in, I don't know, let's use green. So the point that was at -3 goes to +3. Point that was at -6 to -6 becomes to +6. And we have 4, 9 there, and now I can sketch that. Use graphing technology to verify your graph. Okay, so let's get out the graphing calculator. Turn it on. Okay, wait, I can't interact with it on the... Okay, let's go to y equals. I want the absolute value. There is a function on your calculator. It's under math, and it's under num. Whoops, too far. It's under num. Number 1 is ABS, so just hit enter. So I want the absolute value of -3 halves x minus 3. So I'm going to go negative. I like to put my my m value, my slope, in brackets. So -3 halves x minus 3. Okay, and graph the absolute value of that. Hit graph. Okay, so that should match this. It appears to, right? We have some points on here. That's an x-intercept at -2, and this is 1, 2, 3 up here, so we're passing through that point. Okay, so we've used technology, we've verified that this is in fact the graph. Okay, let's go back. State the intercepts of y equals -3 halves x minus 3. Okay, it just says state. We don't have to show any work. What are the intercepts? So the x-intercept is -2. The y-intercept is +3. Okay, remember, intercepts are just numbers, right? They're not ordered pairs. They're not a point. It's not the point of intersection. If I say at what point does the line intersect the x-axis, then you say -2, 0, right? Enclosing that in parentheses. All ordered pairs must be expressed in parentheses. Okay? But intercepts themselves are simply numbers. State the domain and range. All right, let's keep this up where we can see it. So what's the domain? Set of all x. Any restrictions on the x values? There are none, right? So it's just x belongs to the reals. So the set of all x such that x belongs to the real numbers. Range, the set of all y such that, what can we say about y? Greater than or equal to 0, right? Since we're doing absolute value, when we take the absolute value of this whole function, right, and there's nothing else going on out here, right? It's not like -7 or something like that, which would, move the graph down 7. So this is y is greater than or equal to 0, right? We include 0. And you can also say that y is an element of the reals. You can leave that off. So if we're just stating domain, if we're doing it a little more informally, you just say x belongs to the reals. Okay? You can't leave that off when that's all that x is, right? There's no restriction. And then you can just say y is greater than or equal to 0, and that's fine. You know, I don't necessarily need to see the formal range statement. So an informal domain and range statement would look like this. X belongs to the reals, y is greater than or equal to 0. Okay, questions on what you're seeing here? Okay, express y equals negative, is there more? Yeah, there's one after that. Express y equals the absolute value of negative 3/2 x minus 3 as a piecewise function. So what we need to do here is we need to split this function up into two possible functions, right? And it's going to go with, you know, the definition of absolute value again, right? You know, we say it's x if x is greater than or equal to 0, and it's negative x if x is less than or equal to 0. So in this case, this function is y is equal to negative 3/2 x minus 3, okay, if x is greater than or equal to, and we got to go with the x-intercept, right? So in other words, it's just the regular, oh, sorry, actually be less than. It's just the regular, here was the original function in purple, right? It's just the left half of the purple function stays the same. So if x is less than or equal to negative 2, it just is what it is. Right? It's the purple function. As long as x is less than negative 2. When x is greater than negative 2, it's not the purple, now it's the green. Okay? So how do we state that? Well, we say it's this. If x is less than or equal to negative 2. Okay? So it's the purple function if x is less than or equal to negative 2. It's the green function. Now the green function is simply the negation, right? So it's y is equal to the negative of negative 3/2 x minus 3. So it's the negative of the original function definition if x is greater than negative 2. Now in a sense, it really doesn't matter where the equal sign comes, since at negative 2, both of these functions are equal to 0. Right? And negative 2, both of these functions work out to 0. So it doesn't really matter. We just tend to keep it, I tend to keep the less than or equal to sign on the function, you know, just sort of stating the original function, right? Not the negative of that function. Okay, now we should actually try and be a little more, we want to write this a little bit differently than that. Okay, so we want to make an adjustment here. Okay, any questions on what's written there before we go and make the adjustment? No? That's good. So in this piecewise function, actually we just read that. Yeah, no, that's good, sorry. That's fine. So what you do is you just look for the 0, right, of the function, and you say as long as you're one side of the 0, it's the original function. When you're the other side of the 0, then it will be the negative of the original function. Okay? And we're okay to leave it like this. You don't have to turn this into positive 3/2 x plus 3. You can leave it as the negative of. Okay? So let's do one more then. 4, y equals the absolute value of 2x squared minus 5x minus 3. Sketch the graph by first completing the following steps. Okay, so follow these steps. This is what you're going to be doing in the exercises, right? When you're doing this kind of stuff, you're going to follow these steps. You're going to start off by determining the intercepts. The intercepts are the important points, right? Because either the function to the left or to the right of an intercept, the function is either above or below the axis. At the intercept is where there's 0. Functions go through 0 on their way through the x-axis, right? So on one side, they're positive, which means we're just going to leave the function alone. And on the other side, they're negative, which means we're going to take the negative of it, because the negative of a negative is positive, right? It just goes with the definition. Okay, so first, determine the intercepts. So we could generally do that by factoring, right? So 2x squared minus 5x minus 3 equals 0. So basically your first step is try and factor it. If it doesn't factor, then you may have to use the quadratic formula, right? In which case we will generally keep the values as exact values, right? We don't work out values unless it's asked, you know, if it says rounded to the nearest tenth or hundredth, then we'll work them out. Otherwise we keep them as exact. Okay, so 2x and an x, and the 3 is going to go with this, and that's a minus, so that's a minus, that's a plus, and that's your 0. Okay, so you FOIL that out, right? I mean, it's guess and check. I'm just guessing. So 2x squared minus 6x plus 1x is minus 5x minus 3. Okay, so those are, that is the factored form. So the zeros, or the roots, or the solution, or the x-intercepts, right, occur when x is negative 1/2 and x is positive 3. Okay? Watch your notation when you're writing this stuff. You know, you have to write the equals 0 in here. That's part of what you're doing. I've been pretty forgiving on some of this stuff, but you know, don't have to be. You can start taking off half marks if you're just leaving the equals 0 off. Well, then what are you stating? Right? You can't solve something unless it's equal to something. You know, you could just give me the factored form of this, not showing any of that, and then give me this, but that's not really true. Right? If all you write is that, and then follow it with that, this can't follow from it. Right? It's just, here's this, here's its factored form. Okay? So it's important that you make sure that, you know, you show your work, that you're saying, hey, that I know that what I'm doing is solving for when this is equal to 0, and here are my solutions. Okay, determine the coordinates of the vertex of y equals 2x squared minus 5x minus 3. Okay, how do we get the vertex from a... Got to go to vertex form, right? So let's start with 2x squared minus 5x minus 3. Okay, so despite the fact that we're in the third unit, we're still using stuff from the first unit, right? We're still using back to quadratic functions and getting completed square form. Okay, factor out the 2. X squared minus 5 has x. Leave some space. Minus 3 on the end. Okay, come down here. Y equals 2. See, we got to keep the 2. We're not solving this, right? We're not trying to get the roots, so we can't just say, oh, let's divide everything by 2 or something. Right? We have to maintain this. Half of 5 halves is 5/4. Squared. When you square the 5/4, you get plus 25 over 4. You multiply that by 2. It becomes 25 over 2. So we just... So, sorry, 16, right. See? Good thing you guys are here.
My whole life was confused right there.
See? At home, I wouldn't have recognized that till like 3 minutes later, and then I would have had to back up and start over. Yeah, scrub it back and replace it. See here, you can... Okay, 5/4 squared is 25 over 16. Times 2. Did you add 25 over 16? No, I really added 2 times that. I added 25 over 8. I'm going to subtract 25 over 8. Okay? Now this line here is the same as this line here. If you expand this line, 2x squared minus 5x plus 25 over 8 minus 25 over 8, those go away, minus 3. Okay? They're the same. And now we combine. Now negative 3 is minus 24 over 8. Right? Multiply top and bottom by 8. This gives me minus 49 over 8. Okay? Yes, no, take a minute. I'll give you a moment to write this down. So what your question was, how come we didn't do the Y-intercept? So I'm sorry, I left that off. The Y-intercept is negative 3. It's just, that's kind of an easy one to figure out. But still, I did leave it off. So that's right. Okay, so hang on, let's go back here. Turn the intercepts. Y equals negative 3. Okay, so there you go. There's the Y-intercept.
How did you just guess that?
I didn't guess that. The y-intercept is when x is 0. When x is 0, this stuff's going, it's just negative 3. Okay. You don't actually spend a lot of time working out y. Now, here determining the y-intercept from this form is a little bit more difficult. You got to put a 0 in for x, square that and get 25 over 16. Multiply it by 2, giving you 50 over 16. Or sorry, 25 over 8. Subtract the 49 over 8, giving you negative 24 over 8, which is negative 3. So use the intercepts and vertex to sketch the graph of y equals 2x squared minus 5x minus 3. Okay, what were our intercepts? So negative a half, 3. So negative 1/2, that's here. Positive 3, that's here. Negative 3, that's here. The vertex was at, okay, so let's do this. Vertex, 5/4 and negative 49 over 8. So the vertex is at 1 1/4, and what's 49 divided by 8? Like 6, so negative 6 1/8. So 1 1/4 and negative 6 1/8. Okay, so pretty much there's the vertex. Right? We could figure out, we could figure out the x-coordinate of the vertex, right? Because it's halfway between negative 1/2 and 3. That's 3.5 units apart, right? Negative 1/2 minus 3 is negative 3.5, but to get distance we take absolute value. Half of that, half of 3.5 is 1 3/4, so we move 1 3/4 this way or that way. Okay, so let's sketch this thing. Okay, so there's a sketch. Use graphing. Use the intercepts to sketch the graph. Done that. Use the graph of y equals 2x squared minus 5x minus 3. So what do I do with this graph to draw the absolute value graph? Negative values become positive. So I'm going to simply take this vertex and move it up to here. I'm going to take this intercept at negative 3, and that'll become positive 3. Okay? And all we're going to do is reflect this portion like so. And then to draw the graph, these are the invariant points. Right, these guys didn't vary. So the graph in red is the graph of y equals the absolute value of 2x squared minus 5x minus 3. Okay, use technology. Okay, so let's go to our graphing calculator. Change that to y equals. So I still want absolute value. No, wait, I'm going to move over. Absolute value. So it's under math and then num. 2x squared minus 5x minus 3. So that was handy. And hit graph. Okay, and there's our graph. Looks pretty much the same. We could see kind of see it coming down to the negative 1/2. We could see it here at 3. We could see the intercept 1, 2, 3 that it's probably going through. We could, if we wanted to, let's just find the maximum. So second, it just doesn't look like it. It does, it just doesn't look like it. So I'm going to use that as a left bound. That is the right bound. This is the guess. Thought it was plugged in. Negative 1.249999. That's 1.25, right? That's the 1 1/4. And 6.125 is 6 1/8, right? And 49 over 8 is 6 1/8. Okay. Yeah, okay, what else are we doing then? Use graphing technology to verify your graph. Check. State the domain and range. Okay, what's the domain of set of all x such that x belongs to the reals, really?
Other teachers are having trouble with theirs as well.
I just. No, no wait, that's restarting. X belongs to the reals. What's my range? What's range?
Greater than 0.
Yeah, y is greater than or
Equal to?
yeah. Okay, so piecewise function.
Not exactly.
I hate that. Absolute value of 2x squared minus 5x minus 3. You can express that as two different functions, right? One of them is just the original function. And that's where the original function was above the axis anyways. So that's when x is less than negative a half or greater than 3, it's just the original function. In the part of the function where it was negative originally, we take the negative of the function, and those values will be negative if x is between 1/2 and 3. So between 1/2 and 3, it's the negative of the function because these values were originally negative, and less than 1/-1/2, sorry, that's -1/2. Less than -1/2 or greater than 3, it was originally positive, it just stays as it is. Where it was originally negative, we take the negative of it. That's piecewise function.